Example 4-2 is about a circular channel, which we have the length and diameter of the circular channel. So the length is 50 meter. It's a galvanized sewer pipe with a diameter of 0.8 meter. And the head loss was measured from the beginning and end of the pipe, and it was 0.35 meters. So the value of head loss is given to us. Now the pipe is half full, and the shear velocity in the pipe boundary is 0.05 meters. So this is V star. So assuming a fully turbulent flow condition, the question asks us to calculate the Darcy-Weisbach friction factor, average velocity of the sewer, bed shear stress, and channel slope. Okay, so here we have the Darcy-Weisbach equation. Head loss is equal to friction factor, pipe length divided by diameter, V squared divided by 2G. But if you look at this equation, we have two unknowns. So we don't know friction factor and we don't know the velocity either. But then there are two equations for high Reynolds number. So when the Reynolds number is larger than 10 to the power of 5, we have the Karman-Prandtl equation, which is 1 over square root of friction factor is equal to 2 times of the log of Reynolds number times square root of friction factor minus 8. And then we have another equation in the textbook. It's equation 4.16, which is another equations for the explicit calculations. So we can use either of those. So the first one, equation 4.15, is implicit. So it means that you need to do try and error. And then the second equation, which is equation 4.16, is explicit. So it means that you don't need to do try and error. But now here, we can rearrange the Darcy-Weisbach friction factor to isolate velocity in terms of 2G head loss diameter divided by friction factor times length to the power of 1/2. And then the definition of Reynolds number is velocity times diameter divided by kinematic viscosity. So assuming that the kinematic viscosity is 10 to the power of -6 for water, so 10 to the power of -6, then the Reynolds number is also a function of velocity here. So now we have two equations, two unknowns. The unknowns are velocity and friction factor. And then with two equations, two unknowns, we would be able to calculate friction factor and velocity at the same time. So going back to the Excel file. So here we assume that the velocity of the flow is 1 meter per second to see what would be the value of Reynolds number. So diameter times the assumed velocity gives us 800,000. So it gives us an idea that which equation we should start working with first. So in this condition, because 800,000 is larger than 100,000, so we would be able to use either equation 4.15 or 4.16. So I use the 4.15 because it goes with the iterative methods, and then the explicit one is very simple to use. So we have two logarithmic of Reynolds number, which Reynolds number is velocity. So I have 0.8, that's the diameter, and the velocity is 2 times G times head loss times diameter divided by length of the pipe times friction factor. So friction factor is unknown, to the power of 2. So everything's here should go to the power of 2. And then multiplied by nu, so 10 to the power of 6. And then multiplied by the square root of friction factor. Okay, so everything here, you calculate the log minus 0.8. So this gives me the value of 1 over a square root of friction factor. This is the trial version. So I try, and then this is what I give. This is what I get. Okay, so here you see that the value of the friction factor that I use as a trial version is 0.006. So this is the range of the friction factor. So I start with 0.01. And then you will see that what I get from the equation is 0057. So I try that, 0057. I get a new value, 0051. So 0.00517. Okay, so it's 0.005. Okay, very close, 0.00504. Okay, so 0.00505. So you just do the try and error until you get the trial value is the same as what you get. So in this case, you will see that we are very close. Okay, so maybe if I add another 5 here, it converges. Yes, or maybe 5, 8. Yes, so you see that we are very, very close. So now, because I have the value of friction factor, I can do the back calculation, 2G times HL times D divided by friction factor multiplied by the length and everything to the power of 1/2. So this is the velocity that we have. 4.66 is the velocity and the friction factor is 0.056. So there is also another equation that we can use, and that's an explicit equation. And then you will see that there might be a difference between those two equations. So in terms of exam, so I will definitely identify which equation you should use, either explicit or implicit. And mostly in exam, we'll go with the explicit equation. So if the exam is closed for open book exam, then you'll do try and error. Okay, going back to part, so we got the friction factor value of 0.005, 506, and the velocity was 466 meter per second. And then in part C, we already know the value of shear velocity. And then we know the relationship between shear velocity and shear stress, bed shear stress. So density is 1,000 kilogram per cubic meter multiplied by the given shear stress and shear velocity. Then you have the shear stress. And in part D, bed shear stress is the square root of rho g r as 0. 2.5 is equal to a square root of 1,000 times g times r, which is 4 times of diameter multiplied by the slope. And then if you calculate the slope, then you will get 0.0002 or 0.2%.